Today is a big day. Today is the day that all of the group theory that we've done up to this point in the semester is going to pay off. Now, we're not really going to understand what that means until much later on, but it turns out that the theorem that we're about to get a hint of today, and that you'll prove yourselves, is a theorem that's going to have big ramifications not just in the theory of groups, but in the theory of equations and solvability that we're building up this semester. So we're going to finish today with our study of group theory, and our study particularly of the alternating group. And along the way, we're going to see the most important concept that we're going to need to know about the alternating group, and that's what is its conjugacy classes. So we're going to take a moment and review what are conjugacy classes of a group, what's their motivation and why do we care about them, what do they do, how do they behave, and then we'll see that the alternating groups have very interesting properties when it comes to what their conjugacy classes are and how big their conjugacy classes are. So there's two phases to this. First of all, a review of what are conjugacy classes and why might we care about them, and then secondly, what does the specific case of the alternating group look like? So let's get underway. So what are conjugacy classes? In principle, they're a way of regrouping the elements that are in a group in a very particular way. So a conjugacy class is going to be a subset of the elements of a group, which is not necessarily a subgroup itself. In general, it won't be. But that's just another way, besides subgroups and cosets, that we can slice up the elements of, particularly we care about finite groups, so we could do this with infinite groups if we wanted to as well. It turns out that the link that we're looking for is that normal subgroups of a group generally, well not generally, always, are made up of pieces which are conjugacy classes. So every normal subgroup is a union of conjugacy classes in a group. So not only are conjugacy classes the building blocks of a group, they're also the building blocks of normal subgroups of that group. And that's going to be our most important connection. So first of all, what is a conjugacy class? To get some motivation, let's reach back for a moment into linear algebra. In linear algebra, we have this notion of similarity, a similarity between two different linear transformations A and B. So if A and B are linear transformations that take a vector space to itself, so it's an endomorphism of that vector space, we say A and B are similar transformations if there exists an invertible linear transformation U such that B is equal to U inverse times A times U. Right? So conjugating A on one side by U and on the other side by U inverse turns A into B. Now, we care about similarity in linear algebra because two matrices that are similar have a lot of properties in common. Specifically, we can start by noting right away that two similar matrices are going to definitely have the same determinant. So here's an example. Let's take A to be the matrix 2, 0, 0, minus 1, and then I'm going to pick the invertible matrix U to be 1, minus 1, 1, 1. And when I conjugate A by U, I get the matrix B, 1 half, negative 3 halves, negative 3 halves, 1 half. So here are two matrices A and B. They have the same determinant as we can compute in this example. Here the determinant of A is going to be product of the diagonal minus the product off the diagonal is negative 2. Likewise, the determinant of B, even though the individual pieces that make up that determinant look different, miraculously, the determinant remains the same. Why? Well, because the determinant in linear algebra is also a multiplicative function. The determinant of U inverse times A times U is the product of the determinants of U inverse A and U. And since the determinant of an inverse is the inverse of a determinant because of that same product property, that implies that those determinants of U cancel out, and the determinant of B is the same as the determinant of A. Geometrically, what does this mean? Geometrically, remember, the determinant is an area factor. It tells you how the area of, or in general the volume, if we're in more than two dimensions, of a region in Euclidean space changes when we apply this linear transformation to it. So the determinant of A is negative 2, because if we take the unit square, here that has an area of 1, and we transform it via A, we end up with a rectangle whose area is 2 and whose orientation is reversed compared to the original. So the determinant is negative 2 for A. But then the same is true for B. If we take that same unit square and transform it via B, we get a parallelogram in this case, whose orientation again is reversed and whose area is equal to 2. So the area factors and reflections of both A and B in this case are identical. Two matrices that are similar in linear algebra also have the same trace. Remember, the trace is the sum of the entries that are on the diagonal of a matrix. So let's go back to our A and B that we had before, 2, 0, 0, minus 1, and 1 half, negative 3 halves, negative 3 halves, 1 half. What are the traces of these matrices? Well, a trace of A, 2 plus negative 1, is 1. And the trace of B, a half plus a half, is also equal to 1. And the reason that these traces have to be the same for A and B is a little bit less obvious, but it turns out that it relates to this fact, that the trace doesn't actually care which order you multiply your two matrices. In general, remember, if I multiply two matrices A and B in one way versus the other way, I get a different answer. But it turns out that because of the way matrices are multiplied, the entries on the diagonal of AB are the same as the entries on the diagonal of BA. The entries on the diagonal are just the sum of the diagonal elements in the A's and the B's, and so it doesn't matter which order we do that. So the trace of AB is the same as the trace of BA, and as a corollary, that means that the trace of B, which is U inverse AU, if I group the AU and then reverse U inverse with that product, then I can cancel the U's, and I find out the trace of B is the same as the trace of A. So both the determinant and the trace are the same for similar matrices. This is actually a reflection of an even deeper fact, that two matrices that are similar have the same eigenvalues, and therefore not only do they do the same thing to the area, or the volume in general, in the vector space V, they have exactly the same geometric effect. So what do I mean by that? Let's take our two examples again of our matrices A and B, and let's think of what are their eigenvalues and their eigenvectors. Well, the eigenvectors for the matrix A are actually the standard basis vectors, 1, 0, and 0, 1. They're eigenvectors of A because what does A do to them? Well, A does to 1, 0 a parallel stretch by a factor of 2. Why? Because A times 1, 0 is 2, 0. Likewise for 0, 1, A times 0, 1 is 0 minus 1. And so those are the eigenvectors of A. Their eigenvalues are those stretch factors, 2 and negative 1. So the eigenvalues of A are 2 and negative 1, and we can see their eigenvectors, and hence their eigenspaces, drawn in dotted lines in red and green right there. What about B? Well, B has a different set of eigenvectors than A, but it turns out the eigenvalues remain the same. So if I take 1, negative 1, and multiply it by B, what I end up with is 2, negative 2. Therefore, 2 is also an eigenvalue of B. It's just that the eigenvector, 1, negative 1, is different than it was for A. Likewise, 1, 1, if I multiply by B, I end up with negative 1, negative 1, which is a stretch of negative 1 of the original. Therefore, the eigenvectors are different, but the eigenvalues for B are the same, 2 and negative 1, as they were for A. So, in this sense, similar matrices do exactly the same thing geometrically to the vector space on which they act. Right? Here, A was stretching in the x direction by 2 and flipping in the y direction, while B was stretching in the direction of 1 minus 1 by 2, and it was flipping in the direction of 1, 1. So it's doing the same stretching and flipping and rotating and anything else that a matrix can do, a linear transformation can do. It's just doing them with respect to a different basis. So all the geometry, the geometric properties of the transformations are the same. They just happen to act on a different basis of your vector space. So this is the motivation coming from linear algebra for why we might care about conjugacy classes in group theory. Because what conjugacy classes are going to do for us is give us a way to group together elements in a group in general, need not be a group of matrices, but it could be, elements in a group which have a lot of the same behaviors. So let's take a look in our next video at what that looks like by looking at conjugacy classes in the more general setting of groups.